oval. Let me start recording it. So our first speaker is Tetsuo Matoba, who will be talking about poleward boundary aurora, and the second speaker is Larry Lyons, who is going to talk about coupling of mesoscale polar cap flows across the oval poleward boundary to oval disturbances. And folks, as usual, we are holding the discussion and questions until the end of the second talk. Of course, the chat is always open and you can put your questions in or have an offline discussion. So without any further ado, Tetsuo, please take it away.
Okay, let me share my screen.
Looks great.
Can you see my screen?
Yes.
Okay. All right. So my name is Tetsuo Motoba. First of all, thank you for coordinators Sasha, In, and Robbie for giving this opportunity. So today I would like to show you a couple of mesoscale oral forms which develop at the poleward boundary of night side oral oval. From this ISS movie, we can see a lot of dynamic oral feature around the poleward boundary here. So let me start from a brief introduction of what is a poleward boundary and how can we identify the boundary. So this is a cartoon of magnetic field lines in the Earth's magnetosphere. So closed magnetic field lines form loops within the magnetosphere, while open field line extended outward, connecting to the solar wind and the IMF. As a conventional picture, during period of southward IMF, there is a magnetic reconnection open the previous closed magnetic field line at the dayside magnet poles to form open field line. And then the open field line are dragged anti-sunward by the solar wind and then populated in the high latitude lobe region of the magnet tail. The open field lines are eventually reclosed by the night side magnetic reconnection and drift sunward through the closed magnetosphere. This cycle is so-called Danji cycle. On the other hand, in the polar cap, the open and closed field line region are called polar cap and or oval. Therefore, polar boundary separate from polar cap to the oval, which is a proxy of open-closed boundary magnetic field line. So how can we identify the boundary? So mainly there are two ways. One is using in-situ real satellite observation of precipitation particles, which was already described in details by Tom in the last CINEM seminar. To identify the boundary, we can use the characteristic signature of electron and ion spectrum. So for instance, a sharp transition between polar lane and plasma seed electron and grossly dispersed ion structure, which called VDIS. The VDIS is suggested to be a manifestation of magnetic reconnection. Since the VDIS is usually observed near the sharp transition between the poleward and plasma seed electrons, the particle observation makes it possible to identify the boundary more precisely. Another way is using the space-based or ground-based optical observation, giving a reliable proxy of the boundary. So usually we use poleward boundary of red line emission of ground-based all sky imager and poleward boundary of FUV emission of space-based global image. One advantage of auroral imager observation over the satellite particle observation is to provide 2D structure of poleward boundary. So far, the most ideal way to identify poleward boundary would be using a combination of simultaneous spacecraft particle and auroral imager observation. But what I'm showing here is one example of such ideal combination of ASI LIGO and DMSP particle observation of poleward boundary. This is a snapshot of ASI red line emission together with DMSP orbit. The right panel shows the comparison between latitudinal profile of red line emission along the DMSP orbit and energetic electron and ion observation from DMSP. In general, a comparison indicates a good agreement between the particle and optical poleward boundaries. However, as you expect, such a conjunction of simultaneous space-ground observations rarely happens. To study the poleward boundary auroral phenomena, we definitely need more such conjunctions. So from here, let me show you a couple example of poleward boundary auroral phenomena. The first example is poleward boundary intensification, so-called PBI. PBI is one of the most extensively studied poleward boundary auroral phenomena. So this is a movie of PBI captured by a flight light ASI at South Pole. We can see a sudden brightening of poleward boundary aurora, and then it rapidly expands in azimuthal direction as well as in the poleward and equatorward direction. Right panel shows the red line auroral kiogram at Longyearbyen reported by Lorenzen 2004. In this kiogram, we can see faint and bright emission traces. The faint emission indicates polar cap patch, while the bright emission indicates PBIs. What we can see, most of PBIs follow the arrival of polar cap patch at the poleward boundary of auroral orbit. If we assume the polar cap is a tracer of a first polar cap flow, this result suggests the PBIs correspond to the very initial process which happened in the plasma seed in association with the enhancement of magnetosphere convection. So therefore, the PBI are believed to be a part of important auroral dynamics in the subzone initiation sequence like this. But one of the outstanding questions we have is what drives PBI? In fact, if the PBI take place at Poleward boundary, which is a proxy of open-close boundary, so it might be reasonable to consider the PBI are causally related to distant reconnection process. This is a schematic picture obtained from Rockwood 1998, which show the relationship between magnetic topology in the magnet tail PBI in the night side oval and expected rational profile of particle precipitating particle across the oval. So the linkage between PBI and distance reconnection is widely favored, but there are some questions we have to consider more carefully. One of them is spatial and temporal evolution PBI. As I showed in the movie before, PBIs develop in various ways after their initial formation. For instance, some PBI extend equatorward and the other extend azimuthally along the poleward boundary. So it would not be straightforward to explain the variety of such PBI evolution in terms of distant reconnection. In addition, due to very limited simultaneous optical and particle observation, we do not know well about where the PBI are initiated relative to the open-close boundary, and also if the PBI are almost always accompanied by reconnection related VDIS structure. So more recently, another possible mechanism was proposed by Otani and Yoshikawa 2016 as a generation of PBIs. They have considered an ionospheric polarization process at poleward boundary, where ionospheric conductivity has a sharp gradient. When a polar cap flow channel arrived at the poleward boundary, upward and downward feeder current are induced on the westward and eastward longitudinal center of flow channel like this. So these induced feeder current extend much wider in longitude, and peak density of induced feeder current is rather than that of instant feeder current. In this process, they suggested PBI are generated by electron precipitation in the induced upward feeder current region. In general, since the effect of ionospheric polarization is instantaneous, this idea can explain not only the fact PBI are initiated immediately after the arrival of first polar cap flow, but also the fact some of PBI expand rapidly in azimuthal direction. Again, we definitely need simultaneous optical and particle observation to distinguish between those two possible mechanisms. So next, I'd like to show a couple of unique simultaneous optical particle observation of poleward boundary auroral phenomena and discuss their implications. This is the first event using simultaneous polar imager and DMSP particle observation. During a subsome event, polar X-ray imager observed an intense auroral emission spot here. When DMSP passed through the X-ray spot, it observed an inverted V structure here with a relatively high peak energy value over 30 kV near the open cross boundary. The X-ray spot and high energy inverted V structure are suggested to be a result of magnetic reconnection processes. However, using the same event, Ostergaard raised the question of whether such magnetic reconnection could really produce the X-ray auroral intensity. And fortunately, during this event, they used data from the cluster spacecraft located around the magnetic reconnection region. And then they compare the observed X-ray auroral intensity with that calculated from the cluster electron flux observation. They found reconnection-related electron energy fluxes are not sufficient to produce the observed X-ray auroral intensity. So Ostergaard suggested additional acceleration processes is required somewhere between reconnection region and ionosphere, most likely near Earth region. For this event, it might be interesting to consider about what acceleration processes generate the inverted wave structure with such higher energy particle. Because typical inverted wave structure have an energy peak of a few keV or less than 10 keV. So another interesting feature is polar boundary aurora, often urbanic, which called urbanic aurora. Compared to quasi-static aurora arc, urbanic aurora are much more dynamic and usually produced by energy dispersed feed line electrons with energy less than 1 keV. This is an example of urbanic aurora simultaneously observed by THEMIS ASI and FAST spacecraft. We can see when first cross a dynamically moving auroral form near the Poleward boundary. Here, the first satellite observed precipitation feed line electron here. The Rayleigh satellite also observed similar but a more detailed structure of urbanic aurora. Rayleigh is a Japanese satellite which carries both of monochromatic auroral camera and particle detectors with high time cadence. This example was reported by Chaston 2010. Using high-resolution auroral image and electron spectral data from Rayleigh, they clearly distinguish an urbanic and quasi-static auroral form, which developed at Poleward boundary. However, because the field of view of Rayleigh imager is very slow, about 70 kilometers, so it is difficult to tell where the observed small-scale auroral forms correspond to mass-scale auroral form, such as PBI, streamer Bs. So we need a space-based wider field of view camera to detect spatial and temporal development of such mass-scale auroral form. So this is the last example. This is very unique example of PBI identified by a combination of Rayleigh imager and ground-based ASI observation. This event happened in the late recovery phase of substorm. From this movie and this full snapshot, we can see a PBI is initiated around here and then expand as mutual with increasing its luminosity. Just after the PBI initiation, Rayleigh crossed over the PBI. At that time, PBI observed dynamically moving auroral form like this. This is a direct comparison between auroral intensity at Rayleigh point energetic particle flux data. During the PBI crossing, here, this interval, Rayleigh observed energy dispersed electron flux here, less than 1 keV. In addition to such organic electron precipitation signature, we can see inverted like electron flux as well. So this PBI might be caused by a combination of organic and quasi-static accelerated electron precipitation. The particle data also allow us to confirm that PBI occurred just equatable the pole of closed bound. Although this event provides a unique opportunity to study what drives meso-scale auroral form, such observations are actually quite rare. So cinema is one of SMAC's phase A selected missions, and it will offer a valuable opportunity for studying cross-scale coupling and energy transfer in the magnetotale and ionosphere system with remote sensing technique. Cinema consists of 9 spacecraft with an identical set of 3 instruments: auroral imager, particle detector, and magnetic field measurement. So here, let me think about what cinema can do for study Poleward boundary aurora. As cinema has both optical and particle instrument, cinema can give a lot of chance to determine where PBI initiated relative to the open-close bound. That will be help understanding of whether PBI are visible manifestation of this distant reconnection process or ionosphere polarization process. And also, as cinema has a multiple satellite constellation, it can examine how Fidan kind of VDIS structures change during spatially and temporally developing PBIs. Finally, cinema can determine what precipitation particles cause what type of meso-scale auroras. For instance, the particle data can differentiate acceleration processes, organic, inverted V, or their mixing. So in addition, multiple satellite constellation would allow to study how such energy spectra change with dynamically developing meso-scale aurora. As listed here, I do believe if cinema is selected for next phase, it will provide a lot of capability for further understanding of Poleward boundary aurora. That's all I have. Thank you.
Thank you so much. This was a wonderful talk and a very comprehensive overview. As I already mentioned, we're holding the discussion and questions for after Larry's talk. Meanwhile, if you want to use the chat, please go ahead. It's open. Larry, please take it away.
Okay, can you see my screen fine?
Yes.
Okay, it was really exciting for me to hear all this detailed discussion of PBIs, of Poleward boundary intensifications, because, back when I was first started thinking about things going on in the polar cap, me and I think most everybody else thought that polar cap convection was kind of smooth, uninteresting, controlled by the interplanetary magnetic field. And that was all. But then we learned much more that the polar cap really had lots of localized flow structures. Some structures are short-lived, some structures are long-lived, and that they lead to what we call ionospheric flow channels, which is equivalent to plasma sheet flow bursts. So remember, when we're talking about the polar cap and we're looking at things in the polar cap, that's down in here, but that's really on open field lines, so that maps all the way out to the magnetosheath, not just something down here, which is observing it down here, but it maps all the way along. And we talk about flows crossing into the auroral oval, which is a localized driven reconnection. We see it down here in the ionosphere, but we're talking about flows going from the open field lines into the plasma sheet along the entire magnetic separatrix out to the distant X line. So I want to talk about the effects of this quite a bit in terms of forming PBIs and in fact, and streamers, omega bands, substorms, surge development, spatial and temporal development of the substorm, and my latest form of entertainment, which I call laydown events. So, this is the very first paper on PBIs, if you will. Remember, the concept didn't exist, right? There was only substorms, and some people talked about north-south structures, and that was it. There was the concept of PBIs didn't really exist. And so we were sitting there in Sandrestrom and looking at the precipitation and saying, aha, here's the auroral poleward boundary. That's the polewardmost aurora. We see it in the electron density seen by the Sandrestrom radar here as a function of latitude, poleward and equatorward. At the same time, we're measuring the flow velocity, or at least line of sight flows, which are interpreted in 2D. And you see that there's no flow, there's no flow. Then all of a sudden, there's really strong flow going equatorward, and there's no flow again. And we saw these flow bursts every 10 to 20 minutes. And the auroral forms, which we now call PBIs, are located on the westward edge of the flow burst. And when we looked at the Goose Bay radar, that was super darn at the time, one radar, you could see here are the flows, but when you look at the line of sight flows, you can see that the flows extend as far out as we could see, which is 75 degrees latitude, way into the polar cap, across the latitude of the PBI, and into the plasma sheet. So we got the flow going from the oval to the polar cap in a localized region. And we didn't have the name PBI at that time. And we didn't really focus on the fact that the equatorward extension became streamers. So the PBIs to streamers is interesting, but it's all associated with the connection between the polar cap flows across the oval boundary. Now, these were some initial observations of the association between the polar cap flows and the PBIs, and then Ying Zhou back in 2014 did a really comprehensive study of the relationship between PBIs and polar cap flows, and she was really impressed with the association and used the word remarkable in her conclusions about this association. So it's really quite clear that these flows from the polar cap are coming in to the auroral oval and leading to PBIs. So PBIs are common. That means flows are going from the polar cap into the auroral oval. So localized, externally driven reconnection is really common. It's something we really got to think about, like Tetsu was talking about earlier. Okay. Now it's kind of interesting just how to come up with the term PBIs. Initially, this paper was written by Odile de la Beaujardière. She's the one who thought it was important, so she really deserves credit for this. And I thought it was really interesting and started writing a paper on it. My first paper on it, I called them separatrix disturbances because they seem to be occurring at the at the polar cap boundary. And then I brought this up at a GEM meeting back when GEM was like 100 people or something. And the GEM said, you can't call them separatrix disturbances. That's got too much baggage association with it. You got to think of something better. So we came up with this term, poleward boundary intensifications, and GEM people were happy with that. I think we were sitting around a table at lunch or something like that. They said, okay, that's a good one. And then it got abbreviated to PBIs by FTE Zesta. All right. Now, another interesting facet of this connection between the polar cap flows and the auroral oval, in the previous case, you saw what looked like the localized flows, right? Lasted 10 minutes or something like that. Then we started looking at the red line movies from the polar cap all the way into the auroral oval. And this is a red line movie again from Ying Zhou back in 2015. And this is 4 hours, okay? So see this arc here? Come back to where it begins. Here it comes. Still there, it's still there, it's still there, it's still there. This is a 4-hour movie. So if that arc is going across the polar cap, that means there's a localized a flow channel adjacent to it within the polar cap, moving from the dawn side to the dusk side for 4 hours. And as it moves, it connects to a variety of disturbances in the auroral oval. There's no real boundary that you can see when you look at the 6,300 emissions between the polar cap and the oval in terms of the connection to these polar cap arcs, which are, signifying the flow channels. So, it really shows there's long-term, short-term and long-term polar cap flow channels, and you can really just see how they go into the auroral oval and make all the PBI-like disturbances. All right. So let's turn to substorms, which Tetsuo mentioned briefly earlier. And we all had ideas about substorms prior to Themis and the Themis ASIs, but we now know that the substorm onset is the beating, which is a wave structure that grows. So it's a nice classical linearly growing instability, at least linearly growing initially, that starts in the inner plasma sheet. If you're going to have an instability in the inner plasma sheet, you got to change the inner plasma sheet conditions somehow, because it's not unstable before, now it's unstable, so something must happen. So you got this sort of major breakthrough with that Toshi came up with in 2009, where it starts with a PBI, and then you start to see the auroral streamer. It comes around in a curve-like shape, sort of reminiscent of the harangue reversal, and points towards the onset location. Okay, so flow is coming from the PBI, so it must have come in from the polar cap. It's going equatorward, so it's got to have reduced entropy, and it's carrying that reduced entropy plasma in the plasma sheet. This is the ionosphere, but remember it's in the plasma sheet, and pointing right to the onset. So it's changing the distribution of entropy in the tail, and it's in the change of the gradient in the direction required for instability. So this, polar cap flow PBI streamers to onset was seen in hundreds of cases and implies that the polar cap flow channels, starting from the polar cap, lead to the onset. The streamers allow us to infer the flow to onset, but we can really directly test this using ground radars, which we've done for like tens of events. And this is just a fun early example with the Pfizer radar. So here we are as a function of time, electron density along a couple of the radar beams. This is altitude, this is latitude. Brightening here is the initiation of the substorm. This is flow velocity as a function of time and latitude. And here's the substorm onset. And you can see a few minutes before substorm onset, the flow comes in from the pointing southeasterly. So eastward, comes in, gets to lower latitude, lower latitude, lower latitude. It forms a harangue aurora type of shape or harangue reversal type of shape. Onset's right there at the time and location that the flow hits. So that's pretty clear evidence that it's this low entropy plasma that's created in the plasma sheet from the incident of polar cap flow channels that's leading to substorm onset. A kind of an interesting variation of this streamers to onset scenario is what happens along the auroral polar cap boundary at times. In this case, this is a movie of the auroral from one of our earlier papers, and a nice broad local time coverage. Here's the equatorward portion of the oval. Here's the more poleward portion of the oval where the PBIs occur. Now, eventually now we start to see the formation of a nice arc along the auroral polar boundary extending over several hours of local time, but its eastward edge moves equatorward, and as it gets close, we get the substorm onset. Did you see that? Let's try that again. Here it comes, moving equatorward, moving equatorward. There's a flow channel adjacent to that. And when that flow channel gets close, it leads to the onset. And then after the onset, you get the westward traveling surge, and it just continues to move westward by sort of sliding westward along that tilted auroral polar boundary arc, which is then a flow channel coming in from the polar cap. So the flow channel is coming in from the polar cap, like so, leading to the onset, but that polar boundary arc is continuing, so that flow channel from the polar cap is continuing to feed the surge as it's moving westward. One thing you got to think about with any of these substorm events, we're talking about flow coming in from the polar cap adjacent to streamers, and that sort of has a significant north-south component, but substorm onset is east-west, and it expands longitudinally. So why does a north-south like flow lead to an east-west onset, and why doesn't the onset streamers like contact directly to the onset arc? And so that's related to the fact that things are not north-south oriented as you get to the inner plasma sheet. Things become east-west oriented because of the energy-dependent magnetic drift. And one of these low entropy flow channels comes in. This was modeled by Chaiping Wang using the Rice convection model. And if you introduce a bubble at the tail outward boundary, okay, it comes in and starts to become spread azimuthally. The bubble sort of wants to go off towards the dawn side by the electric field drift, but at the same time, magnetic field drift is carrying the more energetic particles towards the dusk side. So the bubble is growing and deepening and expanding in the azimuthal direction, and that's what gives us the east-west orientation. And you lose the very strong north-south flows, which are giving the streamer, so you might not see the streamer all the way in, but it connects to flows that are azimuthal. On the dawn side, it connects to flows that are within the azimuthally expanding bubble in the downward region 1 field line current region. That's what we call DAPS. I'll show you that in some data in a second here. And on the dusk side, the azimuthally enhanced flows are equator of the auroral oval in the downward region 2 current region on the dusk side, which we call SAPS. So this really happens, and you can see that in the radar data. Here is super darn radar data using Bill Bristow's 2D flows or Toshi's later flows. I forget which one at this point. And we start off here with the aurora at the auroral polar boundary, some flows here which are a little bit equatorward of the aurora, so they're SAPs. some flows over here on the dawn side. This is midnight, which are daps. And we see nothing much coming in from the polar cap. But then a little later, we see a flow channel coming in from the polar cap, connects to the daps. A little later, we see it connecting to the daps forward of the downside oval, and then equatorward of it in the SAPS region. And that continues for a few minutes. Then when the flow coming in from the polar cap goes away, the connection and the flows in the SAPS and the DAPS region go away with it. So this really happens. Now, another thing, these flow channels, so this is what happens with flow channels. So another aspect of the flow channel connection from the polar cap that's interesting is its control of the longitudinal expansion. One aspect I already mentioned, and this is that here's one of these tilted polar cap boundary streamers, polar cap boundary arc that's tilted equatorward on its eastward edge. The flow is adjacent to that coming in from the polar cap, at least to the onset, which we see by the beating and the initial linear growth of the waves as we continue to be feeding plasma from the polar cap into the auroral oval, growing that instability. Now, initially, you get the onset and the beating, and that brightening expands azimuthally. That's the azimuthal expansion of the bubble, like you see in the Rice convection modeling due to the magnetic drift and azimuthal expansion of the bubble. But then a little later, the expansion activity forms the bulge, which goes into the polar cap. Okay, and you start to get the westward traveling surge. But if you look carefully, you can see here is that poleward boundary arc, and the flow from the polar cap would be heading right into the head of that surge. And as the surge moves westward, that flow along the auroral poleward boundary continues to head directly into that surge. So this means that it's the impingement of the flow from the polar cap adjacent to that poleward boundary arc, which is a flow channel from the polar cap, likely from the polar cap, that's directly feeding the westward traveling surge and making it continue and expand westward. Now, that's one of the reasons why flow channels from the polar cap lead to the azimuthal development of substorms, but there also can be multiple onsets and multiple PBIs and streamers, which indicate multiple flow channels initially from the polar cap, but more of a north-south orientation, as Sneha Yadov has been recently talking about. All right, this is just another example. This is actually the same example. Now we're just going to look at auroral kilograms as we go from east to west, following this surge as a function of time. So we have our substorm onset. You look at the ground magnetic field. Nothing much happens with substorm onset, which is typical. Then when you start getting the surge and streamers, you start to get the magnetic field depressions. And you can see the poleward boundary arc directly head into the head of the surge. And as we look further and further west, and the surge is moving west, it's later in time, later in time, later time. That connection with the polar cap boundary arc continues, which means the connection to that flow coming in from the polar cap continues. What time scale are we talking here? This is about 8:08 and this is about 8:23. So about 15 minutes of this westward traveling surge. And then the magnetic perturbation on the ground just moves westward with that westward traveling surge being fed by the flow from the polar cap. Okay, now also flows from the polar cap, as I was discussing from the Rice convection model, flows eastward as the DAPS. Okay, and this is a beautiful DAPS example from Jiang Liu. And if you look at the dawn side auroral oval, you see a bright aurora along the auroral poleward boundary. This is pretty common. And here comes a Swarm A spacecraft moving equatorward. Right here at 9:06, hits the auroral poleward boundary. And You have the region 2 currents equatorward of that, they're upward. The region 1 currents forward of that, and they're downward. This boundary is right on the region 1, region 2 field line current boundary, which is what you see in the Rice convection model. And that strong, strong flow comes in exactly at that region 1, region 2 boundary, poleward of this edge of the arc along the boundary of the post-midnight aurora. Okay, so this is strong gaps. Now, sometimes on this arc along the poleward boundary of the post-midnight aurora, we get these waves, which we call omega bands. And initially, Mike Henderson shows that these form from incoming streamers, and thus they're also formed from flow channels from the polar cap. And in fact, you can see that again in Zhang's paper, that here comes swarm spacecraft coming poleward. Here it crosses the omega band boundary. And again, it's right at that region 1, region 2 field line current. And there's very strong DAPS flows in the downward region 1 current region that start just adjacent to this boundary. And of course, this is the most significant disturbance we have on the dawn side. I kind of like this movie because it shows it so nicely. This is midnight over here, so we're on the dawn side. Here's that poleward boundary arc that we so often see. Pulsating aurora, which is just see all the time down here. No problem with that. And so flows coming in from the polar cap and leading to the DAPS. And then we start seeing PBI activity, but it's all staying poleward of the post-midnight auroral region in the region 2 current region. But then with time, starts to extend equatorward as a streamer. And look, it pulls up the aurora from below, and we get that wave pattern along the post-midnight diffuse aurora, which is the megabands. And here comes another one. It comes more equatorward and more equatorward. Misses that area, hasn't quite hit yet. Now the flow channel is getting closer and closer and closer. And we get to the polar boundary, and we just get that amazing interchange motion of the flow coming in and the flow coming out, and the creation of a great big wave moving eastward. All right, one other thing that entertains me on these long-lived polar cap arcs that I was sort of surprised to see when we look at some of these movies. Let's look at this. This is BY greater than 0. So the arcs in the polar cap are moving for a long time from the dawn side to the dusk side. So you can see them moving. And that's just the BY. So now you notice that as the arcs come by, they set off a few little substorm disturbances. This one particular substorm over here. The other arc sets up a substorm over here. So we get multiple little substorm onsets. But now let's follow this arc more carefully. Here it comes, here it comes, here it comes. Then it starts to bend. You can see it bending, becomes nearly parallel to the auroral oval, lays down on the auroral polar boundary, and boom, you get that tremendous explosion off the auroral polar boundary where the polar cap arc and presumably the adjacent flow channel bringing polar cap plasma into the auroral oval sets off this dramatic instability over a relatively broad local time region, which gives a much bigger substorm than we had before. This is another example of that, where we have a polar cap arc, which we see in the red line camera over Alaska. This arc actually started way off over Canada, and it led to a substorm over sort of central to western Canada, which we see here in the ground magnetic field data. And then it turned and laid down on the auroral oval, became parallel, led to this bigger substorm here over Alaska. But what's interesting about here is that this event is that we had good two-dimensional measurements from the superdarn radar. So before this arc comes in the polar cap, you got flow going from from west to east, okay? That's the way it happened to be. But then as this arc comes into the view, you start to see flow from the northeast pushing in just behind this polar cap arc. As the polar cap arc continues to move westward, that flow from the northeast continues to push equatorward, looking like westward and equatorward, looking like it's pushing this arc, okay? And so it's a completely different flow and plasma regime that's coming in. Eventually it turns around. You can see it in the Pfizer radar flows here, coming almost parallel in this direction. And then it lays down and gives you the onset. So this polar cap arc, which is laying down on the oval, is kind of like a weather front. A weather front separates different air masses. So here it's separating different plasma regimes in the polar cap that are slowly moving azimuthally across the polar cap and towards the auroral oval and laying down. And when the new plasma hits the polar cap boundary, we get this broad disturbance. Now, this is just a couple more examples of that kind of laydown event, which indicate the different kinds of things that can happen. Here we have a polar boundary arc that presumably started as a polar cap arc, but we don't have good observations to show it. But as it lays down, you get a contact of over here, over Alaska, and another contact over here, and then over Canada, and the two merge together, and you get this really, really broad substorm expansion. And you can see the very abrupt drop in the magnetic field, almost simultaneously over a really broad region of local time. It's 5.5 hours of local time within just a few minutes as this arc sort of becomes parallel to the auroral oval and lays down on the auroral oval polar boundary, setting off this really broad event. And it need not be just a new substorm. In this case, we got a polar cap arc coming along. It sets off a substorm onset over here, and the flow continues to feed the surge. But that polar cap arc, which is now along the auroral polar boundary, continues to move equatorward and lays down on the oval, gives a new explosion sort of west of and connected to the pre-existing westward traveling surge. So you got kind of a three-stage event. You have your substorm onset, and it's followed by the magnetic perturbations. Then that polar boundary arc actually lays down on the oval, and you get even a broader substorm expansion covering a broader area. And then that surge starts to slide westward along the polar boundary arc, as it very often likes to do, and we see the magnetic perturbation expand westward with time with the westward traveling surge. So in summary, the polar cap wasn't this nice smooth thing. It has a lot of structure. So we learned something new. When we learned something new, it really led to a lot of fun. And these flows can cross the auroral oval, which is localized driven reconnection. It brings new plasma from the polar cap into the plasma sheet, and it can result in lower entropy plasma in the plasma sheet. This leads to the PBIs and the auroral streamers and what we call flow channels in the ionosphere, which is the same thing as flow bursts in the plasma sheet. And this lower entropy plasma, which results from the flow channels in the polar cap, leads to the PBIs, which are the most common disturbances we have in the auroral oval, streamers. The biggest disturbance we have on the dawn side, which are the omega bands, which are associated with these dawn side auroral polarization streams, or DAPS, substorm onset, the subsequent spatial size and duration, including the surge development, and these dramatic laydown events. And so this leaves us with some fundamental questions I think need to be considered. And particularly this is just not being considered. You've got these structures in the polar cap, more localized and long-term. They map along field lines, through the lobes into the magnetosheath, right? And so what's going on in the magnetosheath that's giving these flow channels? What is this connection from the magnetosheath to the polar cap, which is giving us both these long-lived and localized and long-lived structures, which sort of look like weather fronts? So there's a whole bunch of physics going on here. And I've seen exactly one paper on this since we started talking about it, and that was by Toshi and I, so that's cheating. But I haven't seen anybody else looking at this. This is really fundamental to what's driving space weather, just like everything we know, right? And then as Tetsuo was talking about, what is the physics of this interaction of the flow channels at the auroral polar boundary, the localized reconnection, the azimuthal expansion, and how does it lead to PBI and streamer formation and to the reduced entropy in the plasma sheet? So thank you.
Thank you, Larry. Wonderful talk. We have one question already in the chat from Vincent. Vincent, would you like to unmute and ask either Larry or Tetsuo this question? They both talked about the flow channels.
Sure. Yeah, my question's for Larry, and it may be a basic question, but I guess what is the magnetospheric counterpart of those polar cap flows moving equatorward? Is that some sort of disturbance like further down tail that's moving earthward? And then also a follow-up question was, in those laydown events, are there any auroral beads associated with that activation of the onset arc? Thanks.
Yeah, okay. So remember when we're in the polar cap, right, we're on the open magnetic field lines. So that's in the lobe. So there'll be a flow channel in the lobe itself that maps all the way out to the magnetosheath. So you got to think about that in terms of the open field line region of the polar cap, as distinct to the flow burst in the plasma sheet that we see as the streamers. Does that make sense to you, Vince?
Yep.
Okay. And then on the laydown events, do we see the beating? I don't know. We should. And I know one person that might be really well suited to help us answer that question. He might be sitting over there in Alaska by the name of Vince.
Yeah, I was just wondering because, you see the beating a lot of the times with the substorm expansion onset, but not all the time. Like it's not every single event. So I was just curious, but yeah, I could look into that more too.
That'd be kind of fun thing. And we've got these we've got auroral chasers for some of our events that are when we're doing collaborations with super darn high time resolution. And some of these guys may have cameras available at just the right time to catch some of this stuff. So there's some fun to be had there. Good question.
Mike Shumko, go ahead.
Yeah, a very quick hypothetical, or not just simple question, I think, to follow up on Vincent's is when so I guess coming from this from like an MMS perspective, do you see those polar cap flows in the lobes at MMS? Like, do they just appear any distinctly beyond just being away from the central plasma sheet, or how do you detect them in there?
Yeah, I don't. Hope somebody does. I mean, MMS should be able to do that, right? Or not MMS, but maybe, what was it? Cluster might be the one that would be the best for looking at that. But MMS, as it gets into the lobes, it should see it.
Yeah, that's what I was wondering too, because because you can definitely see flows that are going earthward and tailward in the central plasma sheet, but I haven't specifically looked at, in the flows deep in the lobe. So you see stuff in the plasma sheet boundary layer all the time, but yeah, I was wondering if it's just like we haven't been in a high enough information orbit to see that, because I would expect, I guess, from looking at the Dungy cycle, like the magnetic field, you can kind of like swivel around, right, as it's going from the day side reconnection region to the night side. So I wonder, like, have we detected that sort of time temporal progression from high altitude satellites?
Yeah, I mean, that some people should look at. If you're interested, let me know. You know how to do it. I don't know, can MMS observe flows in the lobe in some way? They have enough kind of instruments that can measure in that, cold or low density plasma?
I was gonna say I was almost gonna say yes, but a little hesitant because I know instruments like Themis, they're a lot less sensitive to flows when the count rates are very, very low. So I'm not entirely sure, but anyway, I have a lot of people around I can ask. There's a whole MMS
Yeah.
community.
Well, if it does, it would be really cool because it's really not been looked at and should be, if it can be
Yeah,
done.
because then you can, I think, connect. What I was kind of thinking is, what you think sounds like you mentioned the holy grail of the weather front like thing, where, if you see the flow start on like day side reconnection, catch it coming into the night side, at least through the polar cap, and then see the auroral activity. So anyway, I think that'd be a pretty neat study.
Fantastic. Yeah. Strongly encouraged, whatever you can do.
I have a question. I don't know how to raise my hand. But maybe this is ignorant because I don't know a lot about this stuff, but I think that laydown event is like really convincing and dramatic how it just kind of explodes when that arrives. And I understand the idea of the flow channel, the low entropy flow channel kind of changing the entropy profile in the tail, but do we know why I mean, and there's some instability, do we know what is happening, like why it explodes there? And it's the same place where you're saying the magnetic drifts take over and everything's expanding east-west at that point. Like, why is it why does it happen there? I guess is the question. Is that, do we know from simulations or observations, or what should we be looking for?
Yeah, I mean, observations have seen it in in the plasma sheet at the same time that we see the beating on the ground. So we kind of have seen it. And why does it want to occur where it's east-west aligned and not so much, sort of a transition from the interchange instability to this other instability, which is kinetic. And so why does it want to occur there? And, just for fun, addressing your question, some of these, I've seen some of them where you see the beating right along the east-west arc. Let's say it's on the dawn side. Every once in a while it happens on the dawn side. So it's on the dawn side, and you can see the streamer that's doing it. And then that beating just climbs right up that streamer, by 2 or 3, 4 degrees, sort of becomes sort of, highly tilted towards the northwest direction. So there's a interesting, your question's got one step more complicated answer.
I was wondering what we should be looking for. I mean, those laydown events, that stream is already quite east-west and moving down, and then it hits that pre-onset arc and explodes, it looks like. So I don't know, it's pretty dramatic. So anyway, maybe it's something we should so maybe simulations have something to add to that. I don't know.
If you have 9 spacecraft going over that kind of stuff, you might be able to see. I sort of envision here comes the arc, it's coming down, and the plasma is going to sneak in, around the edges where the little tilt in the arc to get to where the onset is, because the arcs are like at the polar boundary, and that polar the auroral oval just gets really really thin, which you can see in the Pfizer data, maybe a degree or maybe maximum 2 degrees wide. So that low entropy plasma gets in and then spreads azimuthally pretty quickly. So I imagine it'd be sort of like a 2 or 3 break points. Now I'm just waving my hand. And that's sort of what I envision, that arc has sort of, when it's tilting and it's just coming on one side, I envision coming around the edge that's tilting and then spreading azimuthally. So for this, broader ones, I envision it just sort of, I guess on some of the laid out events, I can see it as the laydown starts at the eastward edge and moves westward over 2 or 3, 4 minutes. You can see the onset spreading with it. So like the low entropy flow spilling around the edge of the arc.
And to your question, Robin, Shinatani has a relatively recent paper where he did a detailed study on where the flow breaks relative to where bidding occurs, and brought up some interesting questions related to that. I don't know, Shin, if you would like to comment.
Can you hear me? Okay. So we looked at the divergence of the flow channel from Poleward, and then oral subsome onset takes place not at the demarcation point, but clearly off the demarcation point, indicating that the breaking is not necessarily the direct cause of subsome initiation. So as Larry mentioned, admissal flow, the formation of admissal flow is somehow related to the onset instability, and beads may be related to flow shear or some structure. And so it's maybe coupling between the flow shear and the interchange. And we are just speculating, but that's what or at least our understanding stands for now. And I'm hoping that the cinema will clarify a little bit more about morphologically and place constraint or moderate this kind of bead formation and therefore subsome initiation.
Right. Thank you, Shen. Certainly, lots of room for more studies and observations. More comments or questions? If not, thank you thank you to both speakers for wonderful talks, and thank you for questions and discussion. Please follow SPA newsletter announcements for the next seminars, for when the next seminar will be scheduled. Also, you can check back with our webpage, which we will update as soon as we have it scheduled. And my apologies for technical difficulties. I will reconcile the links, and that link on the website will be where the video will be uploaded, so anyone can watch that seminar at their own convenience. So thank you all very much, and talk to you in a few weeks.
Thank you, Sasha and Ying, for inviting me in. I enjoyed it.
Thank you.
Thank you.